Problem 114. A Boeing 747 airplane has a total wing area of about 500 meters squared. If its weight in level flight is 500,000 pounds, find the average pressure difference between the top and bottom surfaces of the wing in pounds per square inch, or PSI, and in pascals. So let's start by jotting down all of our givens, and we're told that the wing area, which in aerodynamics we typically give the symbol S, so that's what I'm going to be using here, is equal to 500 meters squared, and we're told that the weight of the aircraft, which I'll give the symbol W, is equal to 500,000 pounds, and that's pound force. And we're asked to find what the average pressure difference is on the wings. Now the first thing that I notice is that we're given the wing area in meters squared, which is the international system, and our weight is in pounds force, which is British gravitational system. So here we have some mixed units. So the first thing that I'm going to want to do is to convert these units. And because we want the answer in both the British gravitational, PSI, and in the international, pascals, what I'll do for this example is just convert both of these over to both unit systems. So I'm going to convert the 500 meters squared. So I have 500 meters squared. And to do that, I'll just multiply by a conversion factor, where in 1 foot, there is 0.3048 meters, and so I would just need to square this, and when I do that, I'm of course going to get meters squared canceling with meters squared. I'm going to be left with feet squared. Okay, so this is going to give me 500 divided by 0.3048 squared, and that winds up giving me 5,382 foot squared. And I'll also want to convert the weight, and I'll put that into the international system. And that conversion factor is 500,000 pound force times, in 1 Newton there are 0.2248 pound force, and that gives me a value of 2.224 times 10 to the 6th newtons. And of course we're trying to use this information to find our delta P in PSI and in pascals. So to try and understand how we solve this problem, we first have to think about a free body diagram on our Boeing 747. So we've got flow going over. If this airplane is moving from right to left, our flow will be going over it left to right. And if we think about a free body diagram, we're going to have some forces that are acting on this aircraft. Well, the first thing is that the aircraft has some weight down, W, and the engines would be producing some thrust force forward, just call that T. And then the flow going over that is going to create some aerodynamic forces. And we typically break that down into a lift force, which is vertical or perpendicular to the free stream velocity, and one which is parallel, which we typically call the drag force. Now, our problem, we're told that we're in level flight. Well, if we're in level flight, the airplane is not moving up or down, and so if I were to just sum the forces in the y direction, it would have to equal 0, because again I'm not moving up or down, so the lift has to be balanced by the weight. So this just tells me the lift has to be equal to the weight. Okay, so let's start by trying to understand how we're going to be generating lift on this aircraft. So the majority of the lift comes from the wings themselves, which have some surface area, which I've highlighted here, and that is that wing area S that we were given as the 500 meters squared. And what happens is, as flow goes over this airfoil, which is just a cross-section of the wing, so if I looked at a cross-section of this wing, it would look like this, and my flow is going over it, and the flow going over this shape is going to produce a pressure distribution. And if I look at what a typical pressure distribution might look like over an airfoil, we see that towards the leading edge there is a high pressure towards this, and this will be due to a stagnation point. And then the flow going over the top gets accelerated, reducing the pressure, and the flow going over the bottom creates a higher pressure. So we've set up a pressure difference. And if there's higher pressure perpendicular onto the surface on the bottom and a smaller pressure acting on the top, this will generate an overall vertical force in the lift direction. In this problem, I'm only caring about the lift force and not the component in the drag direction. And so to simplify this, let me think of this airfoil shape in terms of its average pressure and just over a flat plate. And so I have some average pressure going over the top, and I've got some average pressure going over the bottom. Now let's see how we're going to use this information. Well, we have to remember that the force due to pressure acting on any surface is equal to the integral of minus p times the n vector. So that little squiggly line under the n is how I draw a vector symbol. So that's a unit normal and integrated over the area that the pressure is acting on, dA. Now, I have to integrate over the entirety of the surface, and I can break down this integral to just looking at the integration or the force on the top of the body, so integrating over the top minus p and dA, and add to that the contribution from the bottom. So we're going to talk about how we come up with what the pressure force or the force due to pressure is in kind of two ways. The first way I want to talk about this is with a graphical interpretation. And our graphical interpretation is just going to say, well, let's look at this first term here, the integral over the top surface. Well, if I want to find the integral of minus p n dA over just the top, and if I think about this from a graphical argument, that's just the area under the curve. Well, I have to remember that this wing is in 3 dimensions. So if I have some distribution in 3 dimensions, it would look something like this, right? The pressure is acting perpendicular and down towards the surface at all locations. And so if I want to find the area under that curve or under that surface, well, that's just equal to the base dimension, this times this, which is just the surface of the wing, which we called S, and multiply that by the height. Well, the height is just the pressure on the top surface, which is a constant. So that's just P on the top. And I see that since pressure always acts perpendicular and onto the surface, all these vectors are pointed down. So I'm going to have a minus sign, and this is in the negative vertical direction or in the minus j direction. So I have that the force due to pressure on the top surface is minus p on the top times the area of the wing. And if we wanted to do this with a more thorough mathematics, looking at that integral, we can, and let's do that by creating a coordinate system. So I'll create a y-axis and a x-axis, and we'll just give some symbols to the overall length of this thing in the x direction, and I'm going to call that c. Okay, so the value of x at the end here is c, and I'm calling it c because typically we would call the length of our airplane wing the chord. And then the value at the tip here for the length of our wing, I'm going to give the symbol b, and that's because we typically use the symbol b for the wing span value. Okay, so now if I wanted to do this integral with a more thorough mathematical approach, I again say the integral going over the top is minus p times the unit normal times dA. So first I have to think about what is dA. Well, dA is just any little surface, so I'll just create some little surface, call that dA, and my unit normal n is defined as being perpendicular and out away from that surface. So n is going to be just like that. And so if I think about that, well, that's perpendicular to the surface, so that's always going to be pointed vertically up or in the positive j direction. So if it's a unit normal has a magnitude of 1, that's just going to tell me that this vector is just equal to a positive 1 in the j direction, or just equal to j. And I notice that in this problem, because of my simplified analysis of this being a flat plate, that value for n is a constant no matter where I draw one of my differential areas. So this n is just some constant over my area dA. In addition to that, I also know that the pressure is not changing, and so the pressure here is also a constant. And this will help me, of course, with this integration, in that this integral I can then think of as being a double integral, and I'd have to integrate over the x direction, and that's going to be going from my coordinate system from 0 to c, and in the y direction going from 0 to b of minus p times n, the unit normal. Well, we said on the top surface, this is just equal to j. And then dA, well, dA I break down into a differential length in the x direction and differential length in the y direction. Well, since p and j are constants, this integration becomes quite easy. And first I'll integrate with respect to x. So I'm going to have the integral from going from 0 to b minus p times j times the integral of dx, and that's just going to give me x, and I have to evaluate that between 0 and c dy. So this is of course just going to give me the integral going from 0 to b of minus p j, and then this is going to give me c minus 0, which is just going to of course give me times c dy. Well, now I integrate again with respect to y, and this is going to give me minus p in the j direction times c, the integral of dy, if everything else is just a constant, well, that's just going to equal y, and I have to evaluate that between 0 and b, and of course this is going to just give me minus p j c times b. And I can just notice that, well, just to be clear here, we were talking about the pressure just on the top, so I guess I should put a p top here and p top everywhere. And I can also notice that the value of c times b is just the overall wing area, which we had given the symbol s. So in conclusion, we can see now that doing this integral minus p n dA, this is just equal to minus p on the top times s in the j direction. And so we see that from my kind of graphical argument and my thorough mathematical argument, we do indeed get the same exact answer. So similarly, we have to do this for the bottom. So we have minus p n dA, but now we have to do this over the bottom surface. And if we look at the bottom surface, the only real difference is the outward normal, perpendicular and away from the surface. If we're looking at the bottom surface, n is pointed down, or has a value of just minus j. Okay? And of course, that minus sign is just going to cancel with the minus sign in my definition and give me the fact that that force is in a positive direction, or pointed vertically up, which we also know by just looking at these vector arrows, which are pointed up. So just thinking about my graphical argument, this integration would then just give me minus whatever the pressure is on the bottom, minus j times s, or that is equal to p bottom s times j, or it's in the positive j direction. Overall, the force due to pressure is then just equal to, well, I just have to combine these two together. So that's going to give me p bottom minus p top times the area of the wing, and that's in the j direction. And this I can rewrite as just being delta p, or the change in the pressure over the top and the bottom, times the wing area in the j direction. So now let's just revisit our summing of the forces in the y direction. So that was set that equal to 0, and that told us that the lift, which is approximately equal to, how we're treating it as the force due to pressure acting over the top and the bottom surface, and that has to equal to the weight. So this tells me that delta P times S has to equal to the weight, or the average pressure difference is equal to the weight of the aircraft divided by the wing area. And so we just need to now plug in our values to come up with our solution. So first we'll work with our British gravitational system, and that we had 500,000 pounds divided by the wing area, which was 5,382 foot squared, and that's going to give me a value of 92.9 pound per foot squared, or PSF. And the problem asks this solution in pounds per square inch. So to do that, I'll just multiply by, in 1 foot, there's 12 inches. So I square that. That will cancel foot squared with foot squared. And this will give me 92.9 divided by 144, and that's equal to 0.645 pounds per inch squared, or we write that as PSI. Now the second part asked us to find the solution in the international system, and so the weight in this case was 2.224 times 10 to the 6th, and that was in newtons, divided by the wing area, which was 500 meters squared. And so this is going to then give me 4,450 newtons per meter squared, or of course that is a Pascal. So there is your solution. The average pressure difference over the wing of a Boeing 747 is 0.645 psi, or 4,450 pascals.